share? Yes. Go ahead.
Okay. So I thought that the introduction is just informal because everyone knows Edoardo very well. I'm very happy that Edoardo is going to talk about code-based signature, which is a subject that I'm really interested, and it's also very hard. And I'm pretty sure Edoardo will say more about this. By the way, is there such one? Is there such a signature available?
We're getting there.
Okay. I pass it to you, Edoardo.
Okay, thank you, Shi. Yes, so I took the bullet and I'm restarting this seminar series, which is great. But hopefully this kickstarts something important. Yeah, so code-based signature is definitely an open problem that we're trying to close. Yes. So let's see what is happening at the moment, and then if you have questions, oops. See if this works. Okay, so this is the outline of the talk. I'm just going to quickly introduce code-based cryptography, or recap anyway, for those of you that need a little bit of a refresher, and then talk about the traditional approach, which is the hash and sign method, and then the Stern approach, the zero knowledge approach, and then talk about code equivalence and last to conclude. Right, so it's kind of giving an overview of what the directions are in code-based cryptography for signatures. So for code-based cryptography, we obviously intend anything that works with error correcting codes. So I like to talk about error correcting codes because in a lot of situations, we actually use the fact that these codes correct errors. Yes, so a linear code is traditionally defined as a vector subspace of fq to the n. N is traditionally called the length of the code from communication theory, right? And the k is the dimension of the vector space. So these values n and k are kind of crystallized in terms of length and dimension. And the Hamming metric is what we traditionally use to measure this code. So Hamming metric gives us a distance. So we have a weight, which is the number of non-zero positions. We have a distance according to the weight, and then we can define the notion of minimum distance of a code, which is how spaced out the code words are between each other. Yes. Then once we have a metric, we can define the code. I mean, so we have efficient representation for the code. In particular, since this is a vector subspace, we can imagine that we put our vector, our basis vectors in a matrix, and this becomes what we call the generator matrix. Right. So this defines the code exactly like a basis does by linear combination. Yeah? So when you see this, this x times UG, oops. Oh, it is no. Here's the point. So you see here UG, this is a linear combination of vectors to basis. Okay, of course, there are several choices of basis, so we have several choices for generator matrices as well. In particular, the systematic one here has the identity on the left, and this is useful for a variety of reasons. For example, it identifies the communication symbols right in the first k positions. It is also useful, and we'll see later, as like a official, if you want, representation. So every time you have like a code, this uniquely identifies the code. Because every time you have like a different generator matrix, well, that's just an invertible matrix on the left. So you just do Gaussian elimination, you just get back to the same systematic form. Okay, so it's like the unique representative for the code. This is not the only representation of the code. The other popular one is what we call a parity check matrix. So this defines a code as a kernel, right? So code words are the one with product equal to 0. This is what we call the syndrome. And again, we have several choices for this parity check matrix. And in fact, we also have a systematic form for it. And the important thing is that these two things are connected to each other, right? And they define the same code, but then at the same time, because you see that the parity check matrix has the words such that the syndrome is 0, in a sense, all these words have product 0 with the words of the code. So it is a generator for the dual code. Okay, so we can obtain the dual code by swapping the role of parity check and generator. The coding theory class. So you're not teaching, right? And no, so I mean, so as I said before, we like the fact that some codes have algorithms that correct up to a certain number of errors. I mean, this is why coding theory exists, to correct errors, at least ideally, right? And so what is an example? I thought I'd put a quick example if you haven't seen, because otherwise it looks like there's this mysterious thing, right? So what's an example of a decoding algorithm? The one, arguably one of the most important classes of codes, at least in the cryptographic usage, is GOPA codes. And these are defined algebraically. This is a kind of like a simplified version, but essentially they are called GOPA codes. They are defined via polynomial over an extension field. And then what is called a support. So it's a bunch of elements that are not roots. Right? So we choose a polynomial, we choose some elements that are not roots. And then again, it's a simplified description. The proper one goes through like evaluations of polynomials, et cetera, et cetera. But in the end, we get a nice parity check matrix of this form, where elements in each row and column are a certain power of the support element divided by G evaluated in that element. Okay. And then, you know, this defines a parity check matrix over the extension field, but the GOPA code proper is restricted to code words over the base field. Okay, so it corresponds to what we know as a subfield subcode construction. So how do we model errors? Well, traditionally coding theory errors are modeled as an additive vector because again, if Q is equal to 2, then we're just filtering bits, right? But otherwise, we're just adding noise in certain positions. We remember Hamming is non-zero positions, right? So if an error occurs, we modify some of the positions. So it's an additive vector with Hamming weight bounded by a certain value. Okay, so for GOPA codes, T, so this T obviously depends on what codes you're considering, right? The simplest example, you have, for example, Hamming codes, then you can correct one error, right? For GOPA codes, these correct more errors. They correct actually R over 2, where R is the degree of our polynomial. Or actually, in the binary case, we have a better algorithm, we have better property for the code. We actually correct exactly R errors. Right? So it's able to correct a large number of errors, a good percentage of the codes. How does the code correct? First, we compute the syndrome of the received word. You will notice that the syndrome of the received word is, by linearity, syndrome of X plus syndrome of E. So syndrome of X is 0 because X is a code word. E is what we are trying to find. So if we can somehow decode this syndrome, then we can obtain our error, right? So then to find the error positions, we use the magic algebra that is underlying the GOPA codes, and we're able to construct some polynomial sigma and omega, which we call error locator and error evaluator, through this so-called fundamental relation. Okay, so this is again a simplified version of the idea, what is called the Massey algorithm, but essentially, if S is our syndrome, S of X is the polynomial associated to it, and then this polynomial has to verify this congruence modulo, say X to the R. In principle, there are better algorithms that use different polynomials here. But once we recover this, then we're basically done because we just need to find the error position. So because of the particular structure, I don't want to delve into too many details, then the error position corresponds exactly to the roots of the polynomial. So then there's like a root finding step with your favorite root finding algorithm, and then once you find the roots, then you take the reciprocal and then that corresponds to the error position. If the code is not binary, then we have to find the value, and we can do this using omega. Okay, so this is it's an overview of what happens. You know, typically decoding algorithms for various classes of algebraic codes or even non-algebraic codes, you know, work in a similar fashion. You do a syndrome, then you do something, then you do something else, and then there's like several steps, and in the end you're able to recover the error position. Okay, other class of codes, of course, work in different ways, exploiting what is the property of the codes. For example, something we're not going to see in this talk, but LDPC codes, they rely on the fact that the matrix is very sparse. So we don't have any special equation here to satisfy, but rather they have like a lot of zeros and very few ones in the parity check, and then the procedure to recover the error position goes by trying to find these check equations one by one, yes, with an iterative procedure. Okay, so this is just to say we have some magic procedure to the code. Yes, so this allows us to decode when we know that the code has a certain property. On the other hand, if the code is random, so just take a linear full rank of things. This gives me a code, but with no particular sections, it will be the overwhelming majority, right? The probability of hitting something decodable and random is basically nothing. So it is actually hard to decode this. Like, you know nothing about the code, you don't have a special technique. And so this is actually a hard problem, what we call the general decoding problem, right? So given a a word in the space with a target weight, find the error vector such that y minus e is a code word. This corresponds to the coding correcting the errors occurred on y if y is indeed obtainable as x plus a certain vector. Okay, so the key here is that the weight is below a certain threshold. Otherwise, it's always possible to do this. This is actually equivalent to this version, which uses the syndrome and is more popular. What we call the syndrome decoding problem, right? So if we're given a word now in the space n minus k, so it's supposed to be a syndrome of something, find the vector e with that syndrome. Again, you can see that if y is x plus e, then that's the same. So there's an easy reduction from the two problems in both directions. So they're completely equivalent in terms of security. Syndrome decoding was studied first, I want to say, and we have some nice complexity results about it. So it's empty complete in the binary case by Berlekamp and Chris Van Tilburg, and Barn proved it in general for QR codes. Okay, so it's a strong problem to rely on. We also have a unique solution when t is below a certain threshold. This is usually, again, I don't want to go into too many details here. There's this combinatorial bound, which we call the Gilbert-Marshakov bound, or GV bound, and then it's a bound on the size of these spheres centered on the code words. Yes, and so because of this, if we are within this bound, then we have a unique solution, right? So if the number of errors is small, then there's only one code word that could possibly come with it. Yes, this is good, of course, if we try to do cryptography. All right, so what do we need? Well, code-based cryptography will use hard problems from coding theory, right? The ones we just presented. And we just need one more ingredient to create a trapdoor. And this is the indistinguishability. So we need to bridge this gap, because on one hand, we know that codes have some decoding algorithm, right? On the other hand, we know the random codes are hard to decode. So we just need to take a code that we know how to decode and turn it into one that looks random, so that the traditional process in cryptography is I'm going to hide the structure so the attacker can only see the random one and I can see the non-random one, the code, right? Okay, so basically this is kind of like an assumption that depends on the chosen family. Some codes are very easy to recognize, unfortunately. So there's a long history of proposals in code-based cryptography using elliptic codes or Reed-Solomon codes or et cetera, and then the algebraic structure is so recognizable that you can attack the key directly, and it's not secure. So GOPA codes miraculously survived for many years, but we'll talk about this in just a second. And once I have a chosen family, the protocol works in the exact same way, right? So all the protocols in code-based cryptography of this type using trapdoor are choose a code family that you're comfortable with, and then you just hide the structure. Okay, so for brief, because the description could be a GOPA polynomial and some elements, or a sparse matrix, or you name it. Okay, so it's just like there's some private description that gives me access to the coding algorithm, and I just hide it in some way. Okay. So for example, what Michaelis did in 1978 is use binary GOPA codes. And again, to date, we don't know exactly why he chose these codes, right? He never said. Some people said like, oh, he had some like hint that these were going to be strong or something, but now we'll never know because Bob Michaelis passed away recently. So miraculously, or maybe not miraculously, he chose these classical codes, and to date, they haven't been broken in all generality. Okay, so if you hide the private matrix G, which is the one with the coding algorithm, by, for example, scrambling on the left, so you change bases, then you permute the columns. So this brings you to an equivalent code, something we'll see later in the talk, right? So then this is hidden. This looks like random. And then you can do your scheme. Because Michaelis' system used the general decoding problem, you encrypt your code word, you encrypt your message as a noisy code word. So you encrypt it as a code word, and you intentionally add some errors, right? So you sample some randomness, something that is common in cryptography, gives you a probabilistic crypto system. On the other hand, you can do something like the writer crypto system, which is usually considered a dual version because it uses syndrome decoding problem. And the writer initially proposed GRS codes. This later was broken because, again, the codes are too easily recognizable. But the framework works if you just swap out GRS for GOPA or for LDPC or something else, then the framework is sound, right? So it's just the choice of code was unfortunate. But the idea is that instead of encrypting a plain text as a noisy code word, you encrypt it as a syndrome. So you somehow turn your message, which is, I don't know, bit string, into like a fixed weight vector, and and then you compute the syndrome, and then finding the plaintext is the syndrome problem. So there's advantages and disadvantages and differences between the two. But this is just a historical note. I don't want to spend too much time on encryption because it's not about signatures, but it's just like how do we use cryptography traditionally? We do this. Okay, we either add some errors or hide our information. So you could say in general, we hide our information in this secret error vector that we are. Right? So this is not about encryption. So this is basically what we do for encryption, right? We generate a private key and a public key. We encrypt the public key. We decrypt the private key. Yes. So the usual notions are, oh, I'm going to try to recover my plaintext. This is the one-wayness, etc. So again, I don't want to do this. So what we want to do, I want to talk about signatures. And the protocol for signature is similar in spirit, but in opposite fashion. So now the person that signs is the one with the secret. Of course, this should be the secret key here. So you sign with the secret key, and this produces a signature, and then you transmit the message along with the signature. And then when you receive a message and signature, the verifier uses the public information. So this is the public key. Everyone can verify and just accepts or rejects. Okay, so it is not exactly the same, but it's a different type of framework, right? And here we're not concerned about confidentiality. We're not concerned about hiding the message. We're concerned about identifying ourselves, about authenticating. So when we talk about signatures, we have essentially two main attack goals. One is the obvious one, right? So if I can attack the private key, then it's a total break. So first of all, I need to protect my private key. And second, so assuming that my scheme is not dumb and my private key is not vulnerable, what an attacker can do, traditionally what an attacker wants to do is to forge. So produce some valid signatures. And this comes in a variety of flavors. For example, you may want to try and say, oh, I can sign any message, but the scheme is really bad, right? So maybe you're not able to recover the private key, but still it's easy to forge. Or I can forge certain message of a certain type because they're vulnerable. Or even just sign a single message, okay? So because this is the attacker goal, what we want is the attacker to not be able to do this. So when we talk about unforgeability, if, for example, the attacker is not able to sign even a single message, right? That would be the strongest requirement that you have. On the other hand, we have attack models that are similar to the ones that are familiar for encryption with different power to the attacker, right? So we assume that the attacker has only the key. Okay, that's maybe optimistic, right? Maybe the attacker has seen some message signature pairs, not of his choice, but it's very easy to eavesdrop and see that, right? But more powerfully, we assume that the attacker can actually request signature on some arbitrary messages. Yes. And then with this information, it may be easier, of course, to forge and produce some valid signature. So traditionally, what we consider in signatures is, like always, we consider gold plus model together, and EUF-CMA is existential unforgeability against chosen message attacks. And this is actually adaptive traditionally. So the attacker can modify his behavior throughout the, so we again imagine that he can do some signing queries and send a message, get a signature on it, and oh, then these are the messages. So it's quite a powerful model. So this is just to agree on what we mean by a signature scheme and what the target goal is. Okay, so that being said, what's the traditional approach to signature? I want to say that traditionally, the first time people were looking at signatures were doing, okay, we have this task that we have to do. We know how to do encryption. We can turn it around and use the trapdoor to sign as well, right? Because now I'm going to have to use the private key to sign, the public key to verify, but I can kind of do it in this sort of symmetric way, turning things around a little bit differently. Right? So this is what RSA does, for example. And this is called the hash and sign method. In our case, we rely directly on SDP or GDP equivalently. Like, let's say we rely on SDP. It's easy to formulate. So RSA is what we call a full domain hash. We'll come back to this name. Why is a full domain, right? So given a message new, I have my one-way function, right? With the trapdoor and a hash function. I create the signature by hashing the message. So first I take the message and I hash it. This is both for practicality reason to bring my message into the desired format that it needs to be to apply the trapdoor, but also for security reasons, because otherwise it's easy to forge. And so the signature is just, I apply the trapdoor to the hash of the message. Yes. If I do this, then it's clear that to verify, what I need to do is I take the signature, I compute F on it, and then this should be equal to the hash of the message. Right? So then I can take the message, hash it, and verify that these two things are equal. And if the hash function is collision resistant, etc., then this provides security. And so it's a very intuitive way of doing signatures. Okay? Of course, for this we need a trapper. So in our case, the trapper is the coding, and this formulation led to what is known as the CFS scheme, Courtois Saint-André. It was this in 2001. So the idea is that my function is going to lead me into a candidate syndrome. Then the key generation is exactly the same as, say, for McLeese, same idea. I've got a secret code that I know how to decode. I hide the description. For example, I can just take the systematic form for it. And then to sign, I will just apply the hash function and then apply my trapdoor, which is the coding algorithm. So you see, hash the message, apply the trapdoor, bang, that's a signature. And so my signature is just going to be this low weight error vector, right? And then to verify, I just take the signature, compute the syndrome, and verify that it is equal to the hash. Yes. Again, this is the same as, say, RSA signature or a lot of other schemes that use trapdoors. That's how it works. So what's security? Security means that to forge, you need to decode the syndrome. Of course, you don't know how to do that because you don't know the private description. Right? So intuitively, the security depends on syndrome decoding problem. Great, fantastic, very easy. You can already see some like potentially nice things because the signature is very short, it's just like a single vector, right? Everything else is wrong. Okay, so the coding a random word, in fact, is not always possible. So the reason why RSA is called full domain hash, I want to say, is that it just covers the entire domain. So whenever you take your hash of the message and then you apply the trapdoor is, oh, I do hash of the message to a certain power. I can always do this, right? So this is fine, but in case of the coding, I hash my message into a potential syndrome, and then I may end up like somewhere here in this outline. And this was kind of like the best picture that I was able to find, showing the spheres around the code words and the minimum distance. But the reality is that this space around the balls is much, much bigger than the rest. So it's actually a lot less likely to hit a decodable syndrome than to fall into the gap. So this clearly doesn't work very well. So what can we do is just try again. And maybe you can do this in a structured way. So for example, you can add a counter, right? Try hash the message 0. It doesn't work, try hash the message 1. And you keep increasing this counter until you hit the decodable syndrome. Okay, so this is still naive, a bit more structured rather than trying entirely random, but still kind of naive. And because, for example, if you take the original McLeese parameters from 78 that work very well for encryption, then you can see, I mean, this is just an easy computation, and you need 2 to the 260. So this is just for theoretically, right? So if I straight out take the same parameter that I would use for encryption, this doesn't work. So, I mean, clearly I need to do better. So what can I do is change the code parameters, and take a code of the form length is power of 2, and then dimension is n minus mt, so very little. So this is like, it was going to look like a very rectangular code with a very high rate. And then, this code is able to correct errors, so still works for the purpose, but of course, now I get better. So you see, like now my code is 2 to the 16, and the dimension is 2 to the 16 minus 144. And then, I only need 9 factorial decoding attempts. This is still not very good. Yeah, so what this means is that the coding is going to be very slow, very slow. Also, if I do this, then the public key size becomes very big. Okay, so here you see an example of naive in the very first CFS proposal. Yes, of course, the signature is very small. But and this is also for 80-bit security back in the day. They were kind of considered acceptable. Now we raised our standards, right? So what happens is that the signing is very slow. It's in the order of seconds, okay? And the public key size maybe can be reduced if you know a little bit about what happened for encryption using these structured codes with certain properties, like for example, quasi-cyclic or quasi-dyadic. There was a proposal using quasi-dyadic codes by Barreto, Karag, Misowski, and Libor. But then, then we have some problem with algebraic attacks for encryption. The same kind of problems apply here. And in fact, the public key is really not the main concern here. Yes, it's a big public key, but if this was all it was, then we can maybe live with it. But in fact, first of all, because the code is now very high rate, it is not true anymore that this looks random. When the rate is about 1/2, or maybe a little bit more or a little bit less than 1/2, then we're comfortable saying that it's hard to distinguish this from a random matrix of the same size. But this is not true anymore. And these people here found a distinguishing in 2013. Now, this doesn't immediately lead to an attack, but it's still not very good formally to have a distinguisher there. What is even worse is that a generalized birthday attack was presented by Blechenbacher. I suppose you are familiar with this kind of technique, at least some of you, right? So generalized birthday attack. And it basically invalidates all the previous parameters. Now we have to raise our bar. We cannot take t so small as 9. We have to take m equal 15 and t equal 12 just for 80 security bits. This makes the whole thing even bigger, right? We can maybe mitigate this. What people have been trying in the subsequent years is to do some tricks, like for example, using parallel CFS. The idea is to sign multiple hashes at the same time to mitigate this attack. But in fact, you cannot really exploit this. You do it like twice. So multiple is just twice. Okay? So it's really not ideal still. So you double the signature size and the signing time, but maybe you're able to choose more parameters like, it's better, but it still doesn't fundamentally solve the problem. And it's still completely impractical. In the implementations now, this is the last implementation that I'm aware of. Bernstein, Schuler, Schwabe in particular claim that this is the fastest implementation. I tend to trust, for example, Dan Bernstein when he says he has an efficient implementation. So the best that they were able to devise is in the order of several seconds to sign, and the public key is many gigabytes. So we're completely far for anything practical.
So why it is slow in signing? Because the matrix dimension is large?
No, because you have several attempts.
Okay.
Yeah. The main problem is that you're still trying several decoding attempts before you find the decodable syndrome. If you somehow could pinpoint, right, the decodable syndrome, then it's just. But the problem with signing is the entire production of decodable syndrome.
What are the repetition rate? Is it like 5 repetitions, or is it 2 to the 5 repetitions?
No. You saw that with the little parameters that we had before. This is 9 factorial decoding.
Oh, 9 factorial. I see.
And this is because the t is equal to 9.
Okay.
But these are small parameters. Then they became even bigger, right? So 9 became 12, and this is still for 80 security bits. So if you want to do it for 128, which I think is what Bernstein did, then it's even bigger, of course. And then the number of decoding attempts is gargantuan. Okay, and so this is why it's slow to sign.
Do you have to go through the whole procedure every time, and then at the end you decide it's bad, or can you stop somewhere in the middle because you know it's not going to work?
I mean, I don't assume that there is like an immediate way to understand whether the syndrome is decodable or not. So you try, you make a decoding attempt, right? Am I right, Togo? You just, there's no, again, this would be a useful tool if you could just like look at the vector and say, oh, this is decodable, right? Well, that's maybe useful, but also dangerous. So I don't know. So I mean, it's just basically trying to use code-based cryptography in the traditional way, and it doesn't work very well. So can we do better than this? Yeah, so the recent idea was to use SDP, but not with the low weight regime, because this we know, this is what we use for encryption. And the important thing is that when the weight is low, we get a unique solution, right? So if this is my plain text, I want to be able to recover exactly that error vector. But if this is not a plain text, I just need to find a error vector that is corresponding to the syndrome. There may be more than one, but that's fine because it's still hard to find one. So it's still hard to forge. So we can take a vector of very high weight instead of very low weight. So if you look at, the solution is not unique, but essentially there's a range here where we're just doing linear algebra, right? And, then we don't want to do that. But if my weight is here, then it's hard. GV bound is like, around here, then we get the uniqueness, etc. But if I can somehow take a vector of very high weight, then it's hard again to find such a vector. Does this work better? We need to guarantee that the syndrome corresponds to a very high weight vector instead of a very low weight. Of course, the decoding algorithm doesn't work anymore. So we need to decode with some other method. So what we can do is, for example, if we use this type of codes that are called U plus V, which is intuitive, right? So the left part of the matrix is U, and the right part is formed by U plus mother matrix V. Then we can use the generic decoding algorithm like ISD. This is traditionally what is used to attack random codes, right? But we can actually use this on U plus V codes, and it works a little bit better. So there's some little gray area, right? Where essentially this ISD algorithm it's hard for random code, but it's still easy if I know that the code is UU plus V. So it's just going to play exactly in that shaded area, and then you're going to go to the code there. It's not going to be the fastest decoding algorithm, but it's basically feasible, whereas it becomes infeasible for an attacker. Okay, so it's trying to force your way through, and we need to manufacture a high weight syndrome via rejection sampling. And again, you're familiar with this idea. You just sample and then reject and try again. So this was the surf scheme using the binary UU plus V codes. Then the authors found a vulnerability before publication, so they scrapped the entire thing. They came out with Wave, which uses ternary codes. So the problem here was binary. And they also generalized the UU plus V construction, rather than UU plus V, they have some sort of generalization of this. Then Paulo Barreto and I were not sure that this was actually leak-free. So then they changed the way they do the sampling. And then, basically this improves over CFS. It is still the same kind of animal, I want to say. So we have a large key, we have a small signature, the signing is kind of slow. Yes. So if you see the parameters, this is the UU plus V code, right? This is the U, this dimension of the U, this dimension of the V. This is the code length, the field is ternary. You see that the weight is very high, that they try to pinpoint. The public key is 3.2 megabytes. Here we're talking about, again, minimum level, so 128 security bits. Yes. So if you take care of this, like bigger, twice as much as the classic Michaelis key for category level 5. Okay, so it would be even bigger. So if you try to do this for category 5, it would just be huge, right? But even for category 1, like twice as much as the biggest classic Michaelis key you can come up with. The signature is obviously small. In terms of the signing, I mean, there are implementations, but the implementations are essentially advertising, yes, we have fast verification. Yeah, of course, because you're computing a syndrome and then, matching with a hash, but the problem is the signing part, right? So this is quite slow. So it still fundamentally shows the same features. The problem is big keys, low signing. You're really trying to, so it doesn't look like this is a natural way to do signatures. Yes?
What happens if we consider both low weight and high weight at the same time? Is the signing still slow?
What do you mean low weight and high weight?
I mean, like you want to hash and you want to, if you get the low weight or you get the high weight, you accept it?
I don't think this is feasible because to get a high weight vector, you have to really manufacture it. Yeah, you have to choose your parameters in a certain way that guarantees that you're going to have a high weight vector with a certain probability. So if you're shooting for the high weight one, you're not going to find a low weight one. They're not going at random. It's not going to go at random anymore. They're actually like artificially doing some rejection sampling to guarantee this sort of high weight vector there. So it's not going to happen alone. But I think overall, we can maybe concur that it's just like this hash and sign approach works very well for RSA, works very well for other types of problems. For coding theory, we have this problem with, the Hamming weight is just not going to work very well for this.
So are there effort by making Q larger?
That's a good question. I don't know if this helps or not. There is a reason why they chose Q equal to 3 though. Yeah, it would make other things larger, of course, as well. For example, the sizes and things, but I don't think this helps very much.
Q higher, since they have generalized it, so for higher Q it doesn't have any.
The generalization is not on the. I mean, the generalization is on the shape of the UU plus V matrix. Oh. So it's like a block 2 by 2 matrix, and the UU plus V is like the first block is the identity, right? But you can generalize these to a different type of construction that works better. So I mean, there's still stuff to do here, of course, but you're trying to push your way through a ravine of something that is like not really suited for it. So what I like better is the second approach. I mean, at least personally, I think it's easy to agree that. So instead of trying to apply our tractor, we can indirectly rely on single decoding problem and using instead a zero knowledge. So these originally are separating, right? So zero knowledge protocol does different thing. It allows us to prove the knowledge of a secret without revealing what the secret is, or in fact, without revealing anything about the secret. So it's this kind of magic. If you've seen and you've met Veronica, for example, this is what she works in, right? And so we can easily produce what is called an identification protocol or proof of knowledge, right? Values. So this comes from theoretical cryptography, if you want, right? The idea is that you have a secret, you commit to some random data that involves the secret somehow, you then receive a challenge from the verifier, you produce a response, this response looks random, right? It's zero knowledge, so it doesn't communicate anything other thing, and then you can accept, reject. So you prove that the secret, you effectively know the secret, but no one learns, not even the verifier, no one learns anything about the secret. The idea is, of course, is an interactive protocol between like prover and a verifier, but then you can turn it into a signature using this fantastic Fiat-Shamir transformation. So Fiat-Shamir proved that if you do this, you take an identification protocol that is impersonation secure. Impersonation secure means that no one can pretend to know the secret. Yes. Then you can turn it into a signature scheme, and you just have to replace the challenge with like a hash of your commitment and message, right? And so this becomes now non-interactive. So you're playing this game with yourself, then you produce a signature, the verifier verifies in the exact same way. Then you obtain a UFCMA secure signature scheme. Okay, so it's a standard transform. It takes ingredient, secure identification protocol, and immediately turns it into a secure UFCMA secure scheme in the random oracle model. Okay, there's adaptation to the quantum random oracle model. There's a lot of literature on this, but Fiat and Shamir did this in 1986, which is remarkable. Right? So you take this object, you then turn it into a signature. Great. And so verify the identification. So in our case, for code-based, again, there are several other areas of cryptography using different things. For code-based, what we do is that we want to exploit the hardness of finding what it was, which is kind of the same as the coding. Yes, but we don't actually need to have a trapdoor for this. So here is what the Stern protocol, which is the first one appearing, does. The generation chooses a random binary code. This is random, right? We don't need a trapdoor. We have a word that's our secret, and we publish the syndrome of it. So again, the key is protected by SDP. But now I have to convince the verifier that I know this low weight error vector. How do I do? I choose a random vector Y and a permutation. Permutation is because permutation preserves the Hamming weight. So I can publish the permuted version of my secret, for example, and then it looks like a random weight, a random error of that weight. Well, you already know that the error has that weight. So you really learn nothing. If I publish my, if I publish my permuted error, you learn nothing about it. So if you see the protocol, it's a little bit technical, but basically this is my commitment. I commit to the syndrome of Y, I commit to the syndrome of pi of Y, I commit to, sorry, not the syndrome of pi of Y, I commit to pi Y plus E. And then the challenge is one of these three things. And then I either give you Y and pi, well, these are both random, right? I can give you Y plus E and pi, right? Or I can give you pi Y, pi of E. And in any case, you can show that, for example, Y plus E is also pseudo-random because you're just taking E and covering it with a random vector Y on top. Pi of Y is obviously random. Pi of E, again, looks pseudo-random because all you learn is this is a binary word and you just permute it. So you learn nothing, all you learn is the weight. So here you can see the zero knowledge, right? And the verifier is able to verify always 2 out of 3 challenges. And so the idea is that I convince you that I know a low weight word that corresponds to this syndrome, but you learn nothing about the word itself. Okay? Of course, so this is like the initial idea. What is typical about the zero knowledge protocol is that there's a soundness error, what we call soundness error. So 2 big parts of zero knowledge. One is the zero knowledge. You have to learn nothing. The other one is that the protocol has to be sound. What does it mean, soundness error? The malicious adversary can potentially cheat. So he can pretend to know the secret and maybe succeed in some cases. Okay. So for example, here with 2/3 probability, here's an example. If you choose a random Y and pi, and instead of using your actual secret, you use a random X here of the wrong weight, but whatever, right, that satisfies the equation, then you can build C1 and C2 normally, and you can build C3 using pi of X instead of pi of your secret. And then, you basically pass verification in 2 out of 3 cases. If the verifier asks you equal to, then you've been caught, okay? You have similar strategies for passing 0 and 2 or 1 and 2. So always in 2/3 of the cases, you successfully. So this means that a successful verification cannot be trusted. It has to be repeated multiple times, right? Because with probability 2/3, you're cheating. So you amplify this error by repeating the protocol in parallel several times. And essentially the idea is that if you pass verification successfully every single time, then, with a certain probability, you can be convinced that, okay, you actually really know the secret. Yes, because otherwise, sooner or later you'll get caught. Yeah, so you do this until you reach the target level. But of course, then you have to transcript, so your transcript becomes the entire transcript becomes the signature. So this leads to a long signature. And this is the original Stern parameters. If you want only like 2 to the 20 authentication, which admittedly, like it's not the great, maybe works for some application, right? But if you want a signature, this is not good enough. But still, you have to repeat 35 times. And the parameters get bigger. So if you want 128, so these values were proposed here by Stern, this was extrapolated, and you need to repeat like 219 times. The signature becomes gigantic. So good idea, but needs to be done better. So many variants were proposed over the years. Stern, Verong, Boriciro, etc. They all try to use either a different framework. So instead of using syndrome decoding, they can make a list with the code word. And all in all, we are able to bring the soundness down to about 1/2, which is better than 2/3. The signature is kind of pushed, depending on the literature and the computational tricks, around maybe 40 kilobars, something, and we're still kind of far from something that we want to use in practice. Yeah, particularly here. So the main problem here is that the signature is large. So here, the overview of CVE's protocol. I'm just going to do it quickly, but we're going to refer to this later. But the idea is that we use QR codes instead of binary, same setup. Otherwise, our scheme kind of proceeds in the same way. We have 2 commitments instead of 3. We use monomials instead of permutation, so we don't only permute elements, but we also scale them with some non-zero factors. That's because we're working over FQ. But it's similar, yeah. So now our challenge is a random field element, and then you produce this Y plus CE. This again is supposed to hide your error vector, and then your answer is either tau or tau p. So you either return the random isometry if you want, before you were returning the permutation now, or you return the permuted version or the isometric version anyway. So this shouldn't reveal anything about your, right? It has to be scaled, right? Because if you just permute it, now you're over FQs, then you're revealing what the coordinates are, not the positions, but the values. So that's not good. So if you now scale it, you again, you don't reveal anything. Right? So the knowledge is preserved. Here you verify the equation, here you verify another equation with the weight. So a similar idea. You always have to verify the weight somewhere, right? Because the idea is that you're proving the knowledge of a load. So this works better. This was kind of like state of the art up until a few years ago, but still maybe like 40 kilobits in it, not ideal. Okay, so basically all these variants did was push the soundness to 1/2. This still means we have to repeat several times. So we really need something with high soundness. If my soundness is high, not 2/3 or 1/2, then I don't have to repeat them many times, then the signature is not that long. So what can we do about this? The easiest approach is what is used in lattices, right? To use this kind of 3-pass scheme, where the random challenge here comes from your, say, like large finite field or something. You produce something like this, and then you just check using your hash function. So again, this is used successfully when the metric is the small norm for lattices, like this what Persichetti did, and then down the road, I was there when Vadim presented this for the first time, and then that was amazing. And then I now became dilithium, and then there's so much built on. Right? This was very successful. And the code-based setting, our metric is syndrome, right? So now we have a parity check matrix and a random code is a small norm, and the metric is very weak because now, remember the Y is constrained to have low weight because otherwise it's easy to forge. And then this response here actually leaks the secret because you have few non-zero positions here, a few non-zero positions here, you can actually see them right away. So it's just like a simple statistical analysis there. And you can try to fix it. You can try to fix it using maybe quasi-cyclic codes or something, but in the end, still would not say. Basically, Hamming metric doesn't work for this because it's just ones and zeros. The ones are very few. You cannot hope to hide if Y is a vector of low weight. So this paradigm doesn't work because of the metric, essentially. The idea is still valid, though, to use a protocol with high soundness. We just need a different one. And so if we take the CVE scheme, I mean, this was my idea. The soundness error is, as I said, about 1/2, right? But imagine that after the response, I only perform the first check, not the check on the weight. Check on the weight, in fact, I can kind of offload it to this mythical entity, which is called helper. Right? So imagine that there's some guy that checks that the weight is correct. This is fictitious, but the idea is that you can pre-process, right? You can collect samples of this form ahead of time, and then when you receive the response, you just check that what you received was one of the ones that were pre-processed. Yeah. So this allows to, the verification now depends essentially directly on the challenge, and now the soundness is 1/q. So it's much bigger soundness. So this is smart, but of course, we imagine that there is this mythical trusted third party that will pre-process and do everything. Well, we can kind of simulate that, in fact. So this is what we call the MPC in the head approach. This is used in Picnic. It was started in 2007 by a bunch of people that work on theoretical cryptography, and then revisited by Katz, Kolesnikov, and Wang, and now it's become very popular because several schemes use this idea. So MPC in the head means that I do this kind of multi-party computation, pretending there is actually physical party, but it's just one person, and then you're going to ask to reveal exactly one of the parties' computation. This is how you simulate this trusted party. So you do the same keygen for the CV scheme, right? Then you run the helper. Again, this is the prover doing this, but simulating that there's like this kind of this independent third party. You see, compute all the different form of commitments, and then you run the protocol. But so this you verify like in the scheme, and then instead of checking the weight, you just check that Z is well formed among the ones that were previously made. Okay, so this offloads so you just check that this was one of the outside. This way you cannot cheat. You cannot produce here some sort of random vector that verifies the equation. You have to produce a vector that is actually of the form y plus c. So to remove the pre-processing phase, because of course you don't want a pre-processing phase, you use a cut and choose technique. So you repeat this, say, n times, and then you choose 1 out of n. This cut and choose guarantees that your pre-processing is done right, because you don't know which instance is going to be asked of you, right? So there's some techniques here that belong traditionally to the realm of like hash-based signature, for example. So you execute exactly one. So you prepare n setups, you execute one of them, and then you have 1 out of n probability of cheating, essentially, right? Put this together with the other soundness error, that's your soundness error. Traditionally, you can choose n equal q, for example, and then that's the 1/q, 1/n is the soundness error. So this essentially all this convoluted thing leads me to a high soundness. This means I have to do few repetitions, many fewer repetitions than in the traditional CV scheme where the error is 1/2. So you iterate the desired number of times, then you apply facial mean, you got a signature. This is what Picnic does, right? But instead of using code base, they use some sort of symmetric scheme, but the idea is the same. You of course want to run several optimization like Merkle trees to take care of doing the pre-processing. Instead of having like a big list, right? You can use a tree and then check the root. And in the end, it yields much smaller signature. Right now we have something like 17 kilobytes, which is less than half than 40. And it's kind of like pushing towards the right direction. Of course, the Sunny verification time, depending on how much you push the parameters, gets slower because you have several Merkle trees to check and a lot of setups to do. So there's a lot of hashing going on. And maybe you can do this in parallel, but it's still quite expensive. So we have a trade-off here. So we have the theoretical work set. My collaborator Shigeron is working on the implementation. He's the best for the job. I mean, so I trust that he's doing everything to push this. Yes, and then now we just started working with Antoine Jou on a similar. So Antoine came up with a similar proposal using a different mechanism for the MPC, and we're going to see if we can join our effort together and share tricks and potentially put a submission together for NIST. Of course, Antoine Jou, because he is Antoine Jou, has a more efficient scheme. so we'll try to steal some secrets from him, but we're trying to work together on this. So the idea is how we can do high soundness. We have to use some different sort of protocol. This MPC in the head has become quite popular in the last couple of years now. If you know the NIST competition, for example, you see Picnic is like right up there, and that's what it works. Okay, so other thing I will try to say in the last 10 minutes. What else have I been working on? And it comes in the same idea of using high soundness. Yes. So if we go back for a second to the Hamming metric, and I just mentioned before the permutation preserve the weight because you're just moving elements around. So of course, the number of non-zero positions is the same. Right? This is the intuitive way of preserving the weight. But then we have these monomial matrices. Right? They are permutation with some scaling factor. So you move elements around and you multiply by something non-zero. Again, the weight remains the same. This is good when you're working over FQ. So instead of having a permutation matrix with just ones and zeros, right, we have exactly 1, 1 per row and column. You have now a monomial matrix where you have exactly one non-zero element per row and column. In fact, you can use this together with a field homomorphism, if you have some, and then get what is called a semi-linear case. So in a code, you just apply the isometry and get to an equivalent code. I'm sure you've all seen this in your coding theory. And so this idea is that two codes are equivalent if they're connected by an isometry. This is part of a larger framework if you want to having a definition of equivalence between objects. This is valid for lattices too, or for elliptic curves or something. Right? You just have to change what it means to be equivalent. For example, for elliptic curves, two codes are equivalent if they're connected by an isogeny, and it's like, woohoo, isogeny-based crypto. So the idea is that like isogeny-based crypto does exactly this, or we could do this with codes too, right? So we define the permutation equivalence problem by giving two codes C and C prime, we generate a little GG prime. Do we have an S and a P that connect the two codes, or do we not? Okay, of course, in cryptography, for our purposes, we are not interested very much in the decisional version, but more in the computational version, which is like, okay, I know that two codes are equivalent. Figure out what the equivalence is. Yes, but it's the same thing. So this is actually a hard problem. And if we consider monomials instead of permutations, then this is the linear equivalence problem. So permutation is a special case of the linear, which in turn is a special case of the semi-linear, the one where we use the field automorphism. We actually don't use this in cryptography. We just take prime fields, so we don't care about that part. It doesn't really add any security. This is not NP complete, so it's like, okay, not as good as NP, right? There is a result that shows that it's actually not NP complete unless the entire hierarchy collapses. But it's deeply connected with graph isomorphism. There's a reduction in both ways. Graph isomorphism is not great as a reference because it's now solvable in quite some amount of time. So like, what are you doing with this problem? But the truth is that, so we have these reductions. There are very efficient solvers for certain specific cases. So for example, if we can actually connect to graph isomorphism, then the problem becomes easy. But so for example, what we can use to discriminate, because to figure out what the equivalence is the weight enumerator. Weight enumerator just means that you're counting the weight of all the code words. Of course, this doesn't sound practical, right? So we cannot really run. So if we could run it on the two codes, immediately we see what the equivalence is, but we cannot do it. But we can maybe run it on the hull of the code, which is the intersection of the code with this dual. And this is what Sendrie did. And this, if the hull is small, then this actually becomes feasible, and then you can solve the problem. But if the complexity scales with the dimension of the hull. If the hull is trivial, we can actually connect to graph isomorphism, or we can also use algebraic solvers with Grosvenor bases and techniques that belong in that realm there. So the problem becomes easy again. We can also try to look at low weight code words in the two codes. I mean, if they are equivalent, the low weight code was going to be mapped into another low weight code. So we can try and build these two lists of low weight code words in the first and the second code and match them. And this is what Leon was doing in 1982. And then, of course, here we have to choose, exactly what weight are we looking for? Yeah, because if the weight is too high, then we're looking for too many code words. If the weight is too little, then we don't have enough code words to properly reconstruct the permutation between them. This can be improved. So Bulens did this after we presented less. We're kind of proud to say that we steered the community into looking at solving the problem better, because we have reference in cryptography. So when Q is large, we can actually look at the multi-sets of entries. So all of these can actually be tweaked. This is all for permutation equivalence, but you can then adapt it to the linear case. This is to say, like, basically, we have a bunch of easy instances. If the hull is small, we can use the support splitting algorithm of Sendrie. If the hull is trivial, then we have this work that basically connects to graph isomorphism and just solves it very easily. And in general, like, depending on how the code is formed, we can use algorithms to solve it in the easy case. But if our is simple, for permutation equivalence, we take weakly solved dual codes. Then the code is the same as the dual, and then the hull is large, maximum size actually. So then we cannot use any of these approaches here, right? In fact, in the linear case, if you take random codes over FQ, as soon as Q is bigger or equal 5, then these codes are weakly solved. And then, again, these kind of easy approaches are defeated. So then we're down to like the brute force approaches of like Leon. Okay, so we can actually find hard distances. So the problem is not NP complete. There are some efficient solvers. You just avoid those setups, and then you can work with this. So could you actually use it as a standalone problem? Yes, this is what isogenists do, right? For example, I just saw a new paper that came out. I think it was one of the European papers that is trying to set up the ground for doing this with lattices. In fact, saying like, oh, what's the notion of equivalence for equivalence functions, right? So it's basically, and there was a nice talk yesterday in our seminar series Access about this for rank metric code. So what's the equivalence for codes in the rank metric? So every time we have some sort of object, we can define what the idea of equivalence is, right? So of course we don't have commutativity here, which is unfortunate. Permutations don't commute with each other in general, so it's not as good as discrete logarithm, of course. Like discrete logarithm forms a nice group, and we cannot do everything, but we can do some stuff. I mean, some constructions can be adapted. For example, we can build a zero knowledge protocol using the code equivalent problem. This is what we did in 2020. It's the last protocol. And then, of course, when we have that, we can transform it into signature with Shamir. And then we added some tweaks to increase the efficiency, to increase the soundness again. So we use multiple public keys. We can use fixed weight challenges. There's a bunch of computational tricks that you can do here. And so this is what less looks like. I just wanted to give an overview. You set up your key generation to set up exactly the code equivalence problem, right? And then what you do is you commit to a random instance by choosing, say, a random monomial. You then receive a challenge bit and you reply with either the bogus case is like I just give you Q there, or I reply with the actual one that contains the secret. So with 1/2 probability, you're gonna guess, and again we have a soundness of 1/2. Then we repeat, right? But with the tricks that I was mentioning before, we don't have time now. We can increase actually the soundness. For example, using multiple public keys, you then use one of the k public keys, and then this increases your soundness, right? So the verifier can then, obviously verify. So this is exactly like the most naive zero knowledge identification you can do with the discrete logarithms, just translated to this different notion of equivalence. It turns out that the idea is that you're not required to decode here anywhere. So you're just worrying about the equivalence between codes. So the code parameters are much smaller than the ones that we need for codes where syndrome decoding is concerned. Because for those, we have to correct errors. So the code needs to be large enough. Here we can choose very small codes. And this leads to actually small sizes. Of course, one thing that is going to be not small is the public key, because it is like the entire matrix. But, and then, so here you're sending monomial matrices. So these are basically permutations, but they're still relatively compact. So we get small sizes, we get a lot of variability. This is kind of like a table of where we are at the moment. We could be signature. Shibai was asking, is there such a thing as a code-based signature scheme? Yes, we do. So, where we started was, CFS is not even the table because it was completely impractical, right? But Stern was giving us this really long signature with small public keys. And then we've been working on, so Wave is kind of like the best that we can do in terms of Hessian sign. We have this gigantic public key with small signature. And of course, there is no computational times here, so there is no seed signing times, it's just sizes. But this is like the small one, there's the slow one. Right? Everything else is zero knowledge. So we went from very large signatures using the simple approach to decoding with low Hamming. If you use rank metric, this gets better. Durandal is following essentially the dilithium idea. Yes, but they can do it because it works in parametric. The key is big though. So if you look at the public key plus signature, is the order of maybe 20 kilobyte, give or take. So much better, right, than before. GPS is the scheme with multi-party computation that I was telling you before. It's just, or actually these numbers have been trimmed down by a couple of kilobytes. But again, we are trying to do this better. We are now working with that one and this scheme. And the last scheme is quite variable. So for example, we can get to very small signature if we push the key size quite big. So we can get into a wave-like regime if we want to. If the concern is okay, you have your key, no one cares about the key, you just want to do many signings, then this is actually about the same size as that. We can actually push that lower. It's going to be much faster than Wave to sign. So we can kind of match that, but we can also push in the opposite direction and try to minimize the public key per signature. This is what is used, for example, in TLS. So depending on your usage, one thing that because we have these computational tricks, we can balance the scheme as we like it. And so this is kind of what we have at the moment. And again, we're working to improve this and speed it up. There is no decoding involved, right? The entire thing is just computing permutations. So the most expensive operation you have is Gaussian elimination. So it is a lot faster, for example, than isogeny schemes. You have to compute these big isogenies and Okay, so we are getting there. It's getting towards something practical. I guess there's some other schemes that are maybe like 14 kilobytes, 15 kilobytes getting there. We're not going to be as close as the lattice signature, but the idea here is to provide an alternative, especially after recent news that Rainbow is dead. So we really don't have any alternative to lattice signatures. Depending on who you talk to, people trust or not trust lattice signatures. So I mean, here we are building something, yes. So I am just a little bit over time, but I'm happy to. I did not include references, but of course you can ask me for references, right?
Thank you, Edoardo.
So Professor, the hardness is coming from signatures is like Copa codes, so how it's coming?
So
Family of the
depending on the scheme, if you're using the trapdoor schemes, then you use Copa codes or something with the trapdoor. Right? In every other scheme that we've seen, essentially you use random codes, which is great for security purposes. It's very easy to have reductions. And so even for the Stern scheme, use binary random codes, and then you know that this is going to be a hard problem. And no one needs to decode because you're not actually finding the low weight vector. That's your secret. So finding a low weight vector is the task of the attacker to forge. And that's why it's hard. So there's no Copa codes there or anything. You use purely random codes. And now for less and for code equivalence, again, if you use the QRE version with linear equivalence, what we do is just choose a random code, choose a permutation, etc. at random. That's our instance. So everything is randomly based directly on the problem. There's no complicated reduction to that. And so there's lots of good properties because then for example, that product of permutation is pseudo-random, right? So if you take two random permutation, the product is random. So you have a lot of nice results in this set.
And so the syndrome decoding can we see as the inhomogeneous? I mean, it's different, but inhomogeneous is problem because it is the H, E, e to the power T, and
yes, there is a connection to that. Yes, that's the equivalent of cis in a sense. Yes.
so it's the inhomogeneous. Okay.
Yes, exactly. But the two problems are connected, as I think happens for lattices, right? So looking for a word that is equal to a certain syndrome is also the same as looking for a low weight code word. Yeah. So the two problems are kind of related. So the homogeneous, non-homogeneous is more or less the same hardness.
Is there any question from the Zoom audience?
Maybe can I ask something, Edoardo?
Yes.
Hi. So you always use the Hamming weights for as a distance. Is there anybody who any other distance that you can use where you would have better decoding at higher distances?
Yes, definitely. So essentially, it's very well known that in coding theory, you can use different metrics. The famous one is the rank metric, which uses codes over an extension field and then looks at, instead of having vectors, you have, so this is like matrix code. So every vector corresponds to a matrix when you explode it over the base field, right? So this counts then the rank of the associated metrics. So rank metric is kind of like a twin of, so you can do traditional coding theory things with it, but it's also, in a sense, very connected to multivariate system of polynomials. So for me, I always look at it as like sitting in between code-based and multivariate-based. The thing with rank metric is that the coding attacks are not as efficient as the Hamming ones, so you can get smaller sizes. This is why some things work better. As I was mentioning before, the Durandal scheme is using the lattice framework of Lubashevsky and does this. There is a rank metric equivalent of McEliece and a lot of other things. So you can do this with rank metric. You can even do this for equivalence. Instead of having permutations, you have square invertible matrices as your isometry. Whether it gives you better parameters, we're not sure yet. But yes, there are alternatives. There are other metrics that you can look at. Depending how much you want to be, people trust, for example, the Hamming syndrome decoding, because it's been around for so many years, and we know it's NP complete, and we know it's hard to solve because the best thing you can do is like these random solvers, right? Everything else is a little bit novel, so if you switch to like rank metric, people don't trust this as much, and then there are several attacks that you can do coming from multivariate, and then people trust this even less. And so depending on how conservative you want to be, you can push towards new metrics. If it's really giving you better performance, maybe worth it. Otherwise, you may want to go with the trusty thing.
Okay, thanks.
No problem.
More questions?
I mean, as I said before, the other thing I can do is give references if you want to see this.
So what does the LAS stand for?
LAS stands for linear equivalence signature scheme. Yes, it's our, I think it's a very nice avenue. Since we started in 2020, people started looking at it for better attacks, virulence, right? Follow-up schemes, code equivalence, different settings. So there's papers that came out about, oh, can we do this in arithmetic? What's the code equivalence in arithmetic? As I said, there is this paper by, for sure, Leo Duca. He works a lot on this thing. So he published, like, oh, what's the idea of equivalence in lattice? Can we do this? So we generated a lot of interest. Also, we can do different things from the traditional setting with the errors. That again, is the same for codes and lattices, where you have something that is like impure, it's like dirty, right? Then you have to correct these errors somehow. So the idea is that like we can do something like isogenies, like this logarithms that is clean. So it's this group action. So you can do things like group signature, ring signature, some type of things that were not possible to do really before. So we try now to push linear equivalence to do things that we were not able to do traditionally with the other ways. And for the signature scheme, already worked better than all the other signature schemes, essentially, if you want to look at it that way. And for the other things, it works much, much better because if you look at the existing literature for like ring signature, disaster, they were essentially using CFS and it was completely impractical because then, this is derivative of signature schemes. So then you have to like sign many times with people in a group of people. And so it's even more impractical. So it amplifies the impracticality, right? So it is an interesting thing to look at. And it's also a fascinating thing to look at this concept of equivalence between codes, how many map this to that, and several techniques to that. Again, I can give reference for this kind of stuff. We're now working at some security results, and so we're thinking to put this together in submission as well for this. I think they sounded pretty interesting when they saw it the first time. So there's a lot of things to look in that. I'm telling more for the rest of the students, like this is a new, no one really thought. So the idea is that everyone was like, okay, I take McAleese, I have my code, I hide it by taking an equivalent one. That's the extent of how code equivalence was used in cryptography for many years. So now it's like basically new how to do this directly using that as a problem. And in a sense, people still kind of try, if you take the correct instance, the best thing you can do is look for code words of low weight in the two codes, try to match them. That means you're running information set decoding to find these code words a bunch of times. So the security kind of boils down to the same as McAleese, except that this is in a truly random code, not a hidden one, right? So still the best attack becomes like search for code words a bunch of times.
Okay. No more questions. Thanks, Edoardo, again.
See you in 2 weeks. Daniel is talking next. I'll send out some announcements. Let's stop the recording.